Hi, I'm Andy and this is question 3 on the AQA Core 3 paper from January 2006. For more questions on this exam paper, click the eye in the top right corner. In question 3a part 1, it says given that f of x is x to the 4 plus 2x, find f prime of x. F prime of x just means differentiate f of x. So looking at a function here, very straightforward to find f prime of x. We just get 4x cubed plus 2. When you ask a question as easy as this in Core 3, assume that they're probably asking you for a reason. And that reason is that you're going to use your answer to answer part 2 here, where we've got to find the integral of 2x cubed plus 1 over x to the 4 plus 2x. To integrate this, we can use integration by inspection. What you need to notice is that if you differentiate the denominator, you get something that looks a bit like the numerator. What I mean by that is the powers of x are the same. So x to the 4 will become x cubed, and the x will just become a constant. But it doesn't work exactly, so what we need to do is modify the question so that we can have something where the denominator does differentiate to the numerator. So I'm going to keep the denominator the same. And we know from part 1, if we differentiate the denominator, we get 4x cubed plus 2. So this is the function I want to be integrating. But in order for this to be equal to this, I need to bring a constant out the front. And that constant will be a half, because a half multiplied by the numerator will give me the numerator on the left-hand side here. Now that it's in this form, I can use the fact that if the denominator differentiates to the numerator, I can write my answer when I integrate as a log. So I get a half log x to the 4 plus 2x. In part B1, I need to use the substitution u equals 2x plus 1 to show that this integral equals this. So the first thing you should do with any integration by substitution question is differentiate your u function here. So du by dx would just equal 2. And I can now either rearrange this to get du equals or dx equals. In this case, I'm going to rearrange it to get dx equals du over 2. All I've done there is multiplied it by the dx divided through by the 2. The only time when you want to get it dx equals is when you've got a constant. Because if you add some x's on this side and you move them over here, when you substitute it back in, you'd still have x's in your original equation. Now, looking at the substitutions I've got here, if I made them, I could replace the 2x plus 1 with a u, and I could replace the dx by 8 du over 2, but I still have an x that I've got to get rid of here. So I'm going to take this function here, and I'm going to rearrange it to say x equals. It's straightforward enough that we can do it in our head. We'd subtract 1, and then we would divide by 2. Now I'm going to make all these substitutions. So the x is going to be swapped for u minus 1 over 2. The root 2x plus 1 is going to become root u. And the dx is going to be swapped for du over 2. From here, it's just a matter of simplifying. First of all, considering this as a single term, I'm dividing by 2 here and I'm dividing by 2 here. That means I can put a constant of a quarter outside of my integration. Then I need to think about how I can expand out these brackets. I'm going to put an extra step in that you might not necessarily write down yourself doing this question. I'm going to write this as u minus 1 multiplied by u to the power of a half, because this will help me see how to multiply out the brackets a bit easier. So I get 1/4 of u times u to the half. That gives me u to the 3 over 2 minus u to the half. And this is what the question asked us to derive. In B part 2, it says hence show the integral between 4 and 0 of the same function equals 19.9 correct to 3 significant figures. So starting with the integral between 4 and 0 of x root 2x plus 1 with respect to x, I'm going to change this to a new question in which we're integrating u to the 3 over 2 minus u to the half with respect to u. Don't forget also we need a constant of a quarter out the front. And because we've changed variables, we also need to change the limits. So the original limits were 0 and 4, and we know that u equals 2x plus 1. So when x is 4, u would be equal to 2 lots of 4 plus 1, which is 9. And when x is 0, u would be equal to 2 lots of 0 plus 1, which is 1. So our new limits are between 9 and 1. The reason we calculate new limits is to avoid having to substitute back into x at the end and getting a more complicated expression to evaluate numerically. So integrating our function, we'll keep the quarter out the front. Increasing the power gives us u to the 5 over 2. And then we divide by 5 over 2, which is the same as multiplying by 2/5. And for the second one, increasing the power gives us u to the 3 over 2. And then dividing by 3 over 2 is the same as multiplying by 2/3. Next we have to substitute in our limits, which gives us 1/4 of 2/5 multiplied by 9 to the 5 over 2 minus 2/3 of 9 to the 3 over 2 minus 1/4 of 2/5 multiplied by 1 to the 5 over 2 minus 2/3 of 1 to the power 3 over 2. So we'll break the calculation down into steps. So we'll do this bracket here first. We've got 2/5 multiplied by 9 to the power 5 over 2 minus 2/3 of 9 to the 3 over 2. That gives us 396 over 5. We'll do 1/4 of that at the same time. That gives us 99 over 5. And then for the other bit, we don't have to type the whole thing in. 1 to the power of anything is still 1, so we end up with 2/5 minus 2/3. And then we want 1/4 of that. That would give us minus 1/15, but remember we're subtracting it here, so we're going to add 1/15 on here. So for our final answer, we do 99 over 5 plus 1/15. And that gives us 298 over 15, which, if we round to 3 significant figures, is 19.9 as required.